Let's continue now with our discussion concerning the range of a linear map L from V to W. Just to quickly review, we know that the range of L is a subspace of the vector space W. If the subspace is all of W, we say that the linear map L is onto. Now, before we continue, a brief mention of a fact about subspaces of vector spaces. Suppose we have an n-dimensional vector space V. If we have a subspace W of V which has dimension n, then W must be the entire vector space V. That is, there is only one n-dimensional subspace of an n-dimensional vector space, and it is the entire vector space. This fact may seem obvious due to our intuition of working in Rn, but we can prove it using the axioms of a vector space. The proof goes something like this. Fix a basis of W, and of course, under the assumption that W is n-dimensional, the basis has n elements, then by definition, since it's a basis, these elements are linearly independent. And then we need a theorem. The theorem we need is the following. Suppose that the dimension of V is equal to n, then any set of n linearly independent vectors in V is a basis of V. So in particular, this set of n linearly independent vectors is a basis of V, and therefore the span of these elements is all of V, and therefore W is equal to V. So you can spend some more time thinking about the proof of that fact, but we will take it as proven and move on for now. To continue, let L be a linear map between a vector space V and W, and let us suppose that these two vector spaces have the same dimension. Call it n if you like. Now let's first assume that L is 1 to 1. If L is 1 to 1, then by a previous result, I know that its kernel is trivial. I should actually be more careful and be writing the kernel is the zero subspace. And therefore, the dimension of the image is the dimension of V, which we assumed is the dimension of W as well. Let me briefly justify one quick step I took in there. We assume L is 1 to 1, therefore the kernel is equal to 0 by a previous theorem. And now we have this equation that we proved in the previous video that, or at least that we stated in a particular restricted case. We have a theorem that says that the dimension of the kernel plus the dimension of the image is the dimension of V. So if the dimension of kernel in this particular case is 0, then the dimension of the image must be the dimension of all of V, and that's what I've written right here. Now we'll use the fact that we mentioned above. If the dimension of the image of L inside of W is the dimension of W, then the image of L must in fact be all of W. That is, L is onto. So we've shown the following. Under the assumption that V and W have the same dimension, if the linear map L is 1 to 1, then it is onto. Now let's stay with the same scenario, assuming that L maps from V to W and the dimension of V and W are the same. Now let's assume, on the other hand, that L is onto. Well, if L is onto, then by definition the image of L is all of W. Hence, by the same theorem we wrote down above, remember, dimension of kernel plus dimension of image is equal to dimension of V, and dimension of V and dimension of W are the same. We have dimension of image of L is equal to dimension of W, which again is n. So the dimension of kernel of L is dimension of V minus dimension of image of L. That's n minus n is 0. That is, we've shown that the kernel is a space of dimension 0. The only thing that the kernel can be is the 0 subspace. And so we've also shown that if L is onto, the kernel of L is 0, and therefore L is 1 to 1. These two facts taken together give us a proof of the following theorem. Let L be a linear map from V to W, and suppose that the dimension of V and dimension of W are the same. Under these conditions, then we can state the following. If L is 1 to 1, then it is onto, and if L is onto, then it is 1 to 1. Now I suppose to appreciate the significance of the former theorem, it would be helpful to see examples of maps which are 1 to 1 and not onto, or onto and not 1 to 1. So I've given some examples here. The first is an example of a map which is 1 to 1 but which is not onto. X, Y is mapped to X, Y, 0. The second is an example of a map which is onto but not one-to-one. X, Y, Z is mapped to X, Y. Now, the third is an example of a map which is neither one-to-one nor onto. X, Y, Z is mapped to X, 0, 0, 0. So, at a first glance, it seems like the first two examples might provide counterexamples to the theorem. After all, the theorem said that if a map is one-to-one, then it must be onto, and if it's onto, it must be one-to-one. But the important condition for that theorem was that the dimensions of the vector spaces must be equal in order for that to hold. So here, of course, the dimensions of these vector spaces are not equal, so it is possible to have maps which are one-to-one and not onto, or onto and not one-to-one. Also, by the way, I didn't actually verify, of course, that any of these maps have these properties. I'll leave it up to you to verify that this map is one-to-one, not onto. This map is not onto, but not one-to-one, and I'll leave it up to you to verify that this map is neither one-to-one nor onto. Now, for our next important result, let's go back to the general case where L is an arbitrary linear map from a vector space V to a vector space W with two dimensions n and m, respectively, so not necessarily the same dimension. Now, here's our big hypothesis for our following argument. Suppose L satisfies the following property, that any linearly independent set in V is mapped to a linearly independent set in W. Certainly, we can come up with examples of linear maps that do not satisfy this property, so this is a non-trivial assumption we're making. We suppose that any linearly independent set is sent to a linearly independent set. Now, to go on, let's make the following comment. It's easy to generate linearly independent sets in a vector space. In fact, one really easy linearly independent set to generate is the set with any non-zero vector. If you take any non-zero vector V in V, then the singleton set with only one element V is a linearly independent set. This is always true as long as the element is non-zero. Under our assumption for the map L, since this is a linearly independent set, we're assuming that L maps linearly independent sets to linearly independent sets, and therefore this thing, the singleton set with element LV, is linearly independent. And so under our assumption, this is linearly independent, so this thing had better be non-zero. So what have we shown? We've shown that if we take a non-zero element, V and V, then its image is non-zero as well. That is, anything non-zero gets sent to a non-zero thing. And so the only thing that can be sent to zero is zero, i.e., we've shown that the kernel of L is the zero subspace, and therefore L is one-to-one. So any linear map that satisfies this strange property that it always sends linearly independent sets to linearly independent sets must be a one-to-one map. Now let's go the other way around and assume that we have a linear map which is one-to-one. I want to show that L satisfies the same property that we'd started with above. That is, under the assumption that L is one-to-one, I'd like to show that any linearly independent set must be sent to another linearly independent set. Let's see how that goes. So we'll begin with a linearly independent set in V, consisting of vectors v1 through vk. And here's our big question. Is the image of this linearly independent set under L also linearly independent in W? Well, here's the argument that this set is linearly independent. So think back and remember how we prove that a set is linearly independent. We assume that we have a linear combination of the vectors which gives us 0. And then we'd like to show that all of the scalars, which here look like R1 through Rk, must be equal to 0. So why is this true? So let's assume we get 0, and then we can use linearity of L to pull L or factor it out of the left-hand side, so to speak, and write R1 L1 V1 plus R2 LV2 plus through all the way through RK LVK as L of R1 V1 plus R2 V2 plus all the way through plus RK VK. So that's the invocation of the linearity of L. Now, remember we assumed L was one-to-one up here, and so the only thing that's sent to 0 is the 0 vector. So under the assumption that L is one-to-one, this stuff in here must be equal to 0. That's what we have here. And now we use or remember the fact that the original set of vectors v1 through vk is linearly independent. Since this set is linearly independent, all of these scalars, r1 through rk, must all equal 0. So we've shown what we set out to prove. That is that all of these scalars, r1 through rk, are 0. That is, the image of the set v1 through vk is linearly independent as well. So we've gone both directions with these properties and shown or proven the following theorem. If L is an arbitrary map between vector spaces v and w, then L is 1 to 1 if and only if L sends every linearly independent set in V to a linearly independent set in W. And the proof is essentially what was just above. These proofs involved a lot of different elements. Please don't be discouraged if you have to go through the proof several times to put everything together, because I went through it rather quickly as well. Let's consider a special case of a linear map. Consider a linear map, well, consider an n by n matrix A. Now, of course, we can take an n by n matrix A and multiply it by a column vector from Rn and obtain another column vector in Rn. So we can think of an n by n matrix A as a linear map from Rn to Rn. So that's the special case we're considering here. And if we even want to, we can set up some notation. Let L sub Ax be the linear map which is defined by left multiplying the vector x by the square matrix A. Then, as we discussed previously, the kernel of this linear map is precisely the null space of the matrix A, and the image of this linear map is precisely the column space of this matrix A. Now let's put together some equivalent properties that we know about. One, the matrix A is non-singular if and only if its null space is trivial. That is, the matrix A is non-singular if and if the only solution to the homogeneous equation is the 0 vector. We also know that the null space is trivial if and only if the kernel is trivial. After all, the kernel is the null space. But we also know that the kernel of the linear map L is trivial if and only if the linear map is 1 to 1. We proved that these two notions were one and the same. And finally, now we know that if a linear map maps a vector space V to W and the dimensions are the same, which they are here, we know that the properties of being 1 to 1 and onto are equivalent. Therefore, the square matrix A is non-singular if and only if the associated linear map is both 1 to 1 and onto.